I know most of you, but for those of you I don't know, I'm Tom Kane. I'm the faculty director of the Center for Education and Policy Research. For the folks online, welcome. So this session is being recorded, so please keep that in mind when you ask questions. Usually that's a throwaway line, but at our last seminar, one of our speakers said some things about a peer institution in Michigan that she preferred we hadn't recorded. So just keep that in mind. When we're recording this. So when you're asking questions, be aware that this is going to live out there some places. So I would ask that during the seminar, we ask clarifying questions and save bigger picture questions to the end. But I realize we haven't always kept to that standard. And I was talking with Sam beforehand, I could think of some pedagogical reasons why having some substantive questions in the middle would be okay. But so hopefully we'll have 15 minutes at the end, but if we interrupt to ask bigger questions, but if we interrupt Sam too much, we may just bump up against the time. So we're lucky to have Sam here today presenting his paper on the impacts of the Flint lead and water what's the right word? Crisis. But that's not the only kind of work that Sam does. Sam is very interested in using genomic data to predict outcomes. He's writing a book on just how genomic data could or should be used for inferring relationships to longer-term outcomes. So. Welcome, Sam Trejo from Princeton.
Let's make sure this is working. Okay, great. It's so nice to be here. Thank you, Tom. Yeah, I'm very excited. You know, it was during the day I got to meet with a lot of people who I kind of knew of or had only met peripherally. So. I did my PhD at Stanford in sort of the analogous, program at Stanford in the ed school, and so there's a lot of kind of overlap and cross-pollination, so it's really nice to sort of really be here. This is my very first time ever on Harvard campus. So today I'm going to talk about learning from Flint, the psychosocial impact of the Flint water crisis on school-aged children. And I'm Sam Trejo, and I'm an assistant professor in the Department of Sociology and Office of Population Research at Princeton University. So how do you pronounce my name? Yeah, Trejo is fine, like Trejo is fine. Either one is great. Danny Trejo is quite famous. He's got the same name. He's like medium famous. Like I bet a lot of you recognize the photo, but didn't know the name. But he's got my name. And I actually grew up in Austin, Texas, and that's where Danny made his big break, was in the Spy movies. So, a lot of respect for Danny. I'm actually, as Tom mentioned, I'm writing a book currently on sort of social and behavioral genomics and kind of, as well as like the complicated history that humans have sort of regarding notions and ideologies of genetics and genetic difference. And I talk a lot about the difference between race and ancestry in that book, and there's in that chapter, and we actually talk about whether I'm related to Danny Trejo. So if you want to check that out, and it's probably going to be out in like 2 years. Okay, so today I'm going to talk about the Flint water crisis in general, but really quickly, I'm going to do a tangent on this other paper on school shootings, just to sort of introduce the difference and difference framework that we're going to then build off of in the Flint case when we sort of use synthetic control methods. I'm also going to do a hypothetical. It's almost going to look like a lecture, but it's going to be sort of an explanation of what's going on in synthetic control that's visual and a little bit more intuitive than some of the formulas. And then we'll obviously conclude with summing things up in questions. And actually, to Tom's point, yeah, you can ask a question, a subsequent question during the talk if you want, but it better be really good. So the first paper I'm going to briefly talk about was one that I worked on with Maya Rosenslater. She's an economist in the med school at Stanford. It was published in PNAS. So what did we do here? Basically, we asked, does a fatal school shooting occurring in a person's school, a child's school, affect her mental health, and if so, by how much? So there's over 240,000 students have had a shooting in their school in the last 20 years, but very few students have been kind of directly, physically impacted by shootings in their school. So basically, there's this question of spillovers, or there's this question of indirect costs. So is the sort of negative cost of having school shootings greater than just the physical harm done, by the violence? Is it sort of trickling off into mental health outcomes? Is it making the spaces feel unsafe? The key central question of causal inference, which is probably obvious to y'all, but I've given this talk to a lot of audiences, is the students, schools, cities that had school shootings are different than those that did not experience school shootings. And so, basically we're confounded. And to identify a causal effect, we have to construct the counterfactual. So what would have happened, in the absence of treatment? And again, this is all nested in the potential outcomes framework, which I think is old hat for y'all. So what did we do in that paper? So here we have a figure. On the y-axis is basically rate of antidepressant use among children. And then on the x-axis, we just have centered time on the event, on school shootings. And so we're basically looking at all shootings that happened in sort of the early 2000s, about 2005 to 2015. And basically, we don't actually know which school the kids went to, but we know where they live. And so we're basically looking if the schools that are within 0 to 5 miles of a fatal school shooting, do they experience a change sort of pre and post after the shooting? And so you can see from this first differences, they do, right? Like, as we're sort of going up, there's a positive trend generally, just secularly, antidepressant use is rising among children, but then there's sort of a spike that happens when the shooting occurs. But we don't know if this is a causal effect necessarily, so we have to find a comparable control group that shares the same pre-trend, right? The same slope in the pre-period. And so this is kind of called the common trends assumption, and difference in difference relies on this common trends assumption. So what's our comparable control group here? Here we just use students living 10 to 15 miles from that school. And so is the common trends assumption here met? It looks like it is, right? The slope of this top graph looks pretty similar in the pre-period to the slope of the bottom graph. So then we can go ahead and use our difference in differences methodology, right? Basically what we're doing is we're taking this post-trend of the control group, and we're going to slide it up to be the treated group's counterfactual. So we're just going to slide this red all the way up, and now we have sort of an estimate of what the treated group would have been in the post-period, and we're going to call that difference between sort of what actually happened and what we thought would have happened in absence of treatment. We're going to call that the causal effect, and that sort of is the 20% increase here that we identified in that paper. Anyways, so this is called difference in differences. I think this is pretty familiar to everybody in this room, but if not, we're going to build off this in the talk. So the talk is really about this paper, the psychosocial effects of the Flint water crisis on school-age children. And it's joint with Gloria Yemens Maldonado and Brian Jacob. Gloria's at the University of Texas Med School, and then Brian is at University of Michigan. So this is a project I actually began as a graduate student. A part of it was part of my dissertation. Later, sort of they added data, new co-authors. I've had the chance to present it in Flint and at conferences, and now it's currently an MBR working paper, so you can check it out. But before we actually move on to the causal inference design of the study, it's important that we kind of have a shared understanding of what happened in Flint and what were the key events. Yeah, question?
Spend 2 seconds trying to make that go away.
Thank you. Okay. So the timeline of the Flint water crisis. In 2011, the city of Flint is bankrupt, and Michigan appoints a string of emergency city managers. And these managers basically supplant the control of the local government in order to sort of make it solvent. If anyone has watched Parks and Recreation, that's basically the premise of that show. Here we go, we're good now. So then in 2014, in order to save money, the Flint water supply is switched from Lake Huron, which is basically the Detroit water service, that Flint would purchase its water from Detroit, to the Flint River, which runs through the heart of the city. And the Flint River water was corrosive and improperly treated. And lead from pipes began to leach into the tap water. And almost immediately, residents noticed sort of changes to color, odor, taste of their water and started complaining. So here's an example. These are like real water samples from Flint. In the aftermath, you can see on the date there, that was in 2015. So a good time after the switch. So then in 2015, though, around the same time as that picture was taken, the city of Flint officials are publicly insisting that the water is totally good to drink. So the mayor of Flint even went on TV and drank the tap water on local news. This is him doing that. I'm sure he came to regret it. He did not get reelected.
He's cringing.
Yeah. Yeah, and it's interesting that he's using like an opaque mug, right? It's almost like they're trying to like cover up the color of the water.
Yep.
I don't know. So basically, this is an important part of the timeline, though. There's a period after the water switch where sort of the state and city officials are encouraging people to continue using their water and claiming that it's safe. And it wasn't until early 2016 that the crisis is acknowledged and a state of emergency is declared. The EPA comes in and sees imminent and substantial endangerment. The National Guard is called in to distribute bottled water. And then the city of Flint begins replacing its lead service lines. So these are pipes that connect individual houses to the bigger water main and historically have been made out of lead in many US cities. And this is actually nearly complete, and we're going to use some of that data. So, but, the punchline is that when the crisis finally broke, when most of us, at least any of us who aren't from Flint or don't have connections to Flint, learned about it, the Flint citizens had been exposed to lead-contaminated water for about a year and a half. And this is the part that's probably very well known to all of us, but this majority black city quickly became a symbol of government negligence and racial injustice. And the percent of children with high levels of lead in their blood doubled. So this is, the CDC's threshold for what sort of is considered to be a dangerous level of lead. So it went from 2.5% of children in Flint to about 5%. And there was a mean increase of 0.5 micrograms per deciliter. This is like a blood lead level measure. And just kind of hold that number in your head, or just remember that I mentioned it here, and we're going to come back to that. And I think something to highlight is Flint was very high profile, but actually lead poisonings like what happened in Flint are not uncommon in the US. So here is a New York Times article from 2018, just down the road from my university, Princeton, in echo of Flint, Michigan. Water crisis now hits Newark. Other cases in DC, Pittsburgh, Providence, Philadelphia, Milwaukee, and more over the last 20 years. So many of these didn't have the level of government denial or as such of a discrete switch from good to bad water that Flint did, and so they didn't necessarily raise as much attention, but they're still happening. So why is lead a problem? Lead is a neurotoxin, so even very low doses negatively impact cognition and behavior. Basically, we haven't found a safe level of lead, even though there is an official CDC guideline. And lead largely affects kids who are under the age of 5. In the US and around the world, there are two main sources of lead exposure: paint and plumbing. I guess we're going to focus on plumbing here. It's about a quarter of lead exposure comes from plumbing, so paint is really the main source. But paint has actually been largely a success story in the US. There's been great reductions in lead poisoning from paint in the last 50 years. So lead contamination from plumbing requires two things. One, there has to, buried beneath the ground, kind of hidden away from our eyes often, there's lead pipes. Lead was actually one time a preferred material for making service lines. There was a city of Flint decree that required all service lines be made of lead in about 1900. And then also, so you need lead pipes underneath the ground, sometimes in houses, or lead fixtures, like the sink or faucet can sometimes be made of lead. And then corrosive water. So this really makes lead in water uniquely difficult to contain because it's not something that we can test for at the plant. It enters through each house's service lines, right? So we actually don't totally know which houses have lead service lines and which don't, and it can be very expensive to find out. And yeah, again, we can't measure it at the treatment plant. So in terms of the social patterning of lead, there's a pretty large literature on how both lead paint is socially patterned, but I think lead plumbing is also socially patterned, but I think in a really different way. So for paint, the social risk is more conferred at the household level. You have to be living in an old house, a house that was constructed and painted when lead paint was still common, so over 40 years ago. And then also, it has to not be remediated, and largely has to have pretty deteriorating paint. So that if there's big chunks of lead paint that are crumbling to the ground and children are, for example, putting them in their mouths, that's sort of the risk for exposure. For plumbing, I would argue that the social risk exists a little bit more at the community level, but there's both community and household factors that matter. So the question is, do you live in a house with lead pipes? So that's a household level factor. In a municipality that fails to properly treat its water. So if we think about the cities that I listed, Flint, Newark, Pittsburgh, Providence, DC, Philadelphia, Milwaukee, it's not a very random set of cities, right? These are cities that have large Black and Providence, Latino populations, and historically received a lot of Southerners from the Great Migration, and in recent years have faced a lot of industrial decline and poverty. So there's something about these cities that leads to the water mismanagement, or increases the risk of water mismanagement, that combines with the lead pipes to create these crises. So in terms of a theoretical model, we have these kind of structural forces. Here we're talking about race, poverty, industry, geography, and those are increasing the likelihood of failure of particular public institutions. In this case, it's water treatment. And then that is raising the risk of environmental health exposures. Here we're talking about lead, and that affects child development, and we're talking about, in this paper, educational outcomes. So what is the goal of the project? I mean, first off, we want to quantify the costs of this sort of high-profile and important historical event. Education records are actually probably our best outlet of making sort of a decent causal inference here, because they're really the only longitudinal data that's available for everybody in the city of Flint. There's very little private school attendance in Flint that exists before and after the crisis, so we actually have a pre-post comparison. And a high level, you can see this in the title, the psychosocial effects, but we're interested in impacting everything that went into the crisis, sort of not just the lead, but also sort of maybe these other more indirect effects. So in particular, we want to explore the social effects of living in a town experiencing a crisis. So people in Flint might have felt stigmatized, marginalized. There was documented social unrest. And this has implications beyond lead, even beyond Flint. We also might be able to learn about the cognitive and behavioral effects of lead. Most causal studies of lead poisoning look at lead treatment or remediation programs. And so they're looking, and those are targeted at kids under the age of 5 who are thought to be at the highest risk. So there's comparatively much less study of kids who are above the age of 5. So this is, I think, one of the first, or if not the first, causal study of lead poisoning in older children. And as the title suggests, we're using school-age children, people who show up in our education data. And maybe highlight the burden of lead pipes in the US today. So 20 million Americans still receive their water through lead plumbing. Especially in the older parts of the US, lead plumbing is pretty common. So what are we actually going to do? How are we going to answer these questions? We implement 2 parallel empirical strategies. So one is a between district analysis. So here what we're going to do is we're going to compare Flint, or compare children living in Flint and therefore exposed to the crisis, to similar children living elsewhere in Michigan before and after the crisis. And so what could drive any effects we detect here? Here the mechanisms are quite broad. It could be the lead effects, right? So moving from sort of pre to post, we expect sort of increased exposure to lead in Flint and not other places. But we also expect other things like stigma, marginalization, civil unrest. And so all of this is going to be baked into our between district estimates. But then we also have a within Flint analysis. So here we're going to compare Flint children who live in homes that had lead pipes to Flint children who live in homes with copper pipes before and after the crisis. And this is really, mechanism-wise, this is quite narrow, right? The only difference we systematically would expect between these 2 groups is exposure to lead. And so to the extent that the lead matters, it should show up in the within Flint analysis. And this, by doing both of these all at once, we're able to sort of separate out the lead effects from the everything else. And we can't really, read in, we don't have any way, I'm just going to highlight early on, we don't really have a way of unpacking what's in everything else, but we're just able to separate out lead from it, the sort of direct biological exposure to lead. So we're going to use Michigan Departments of Education's restricted use longitudinal education records. This is good, high quality data. So it has all Michigan public school students. Just to give you a ballpark of our sort of the exposure group sample, we have about 17,000 students living in Flint each year. It's really important that we use the individual level data here because a really high fraction of children living in the city of Flint and therefore exposed to the crisis actually attend charter schools. Some of those charter schools are actually outside of the city of Flint. About 50% of, basically public school students in Flint attend a charter school. So, we have important demographic characteristics here. Student address will be really useful for this pipes analysis where we actually match, individual students to the specific material of the service lines to their home. And we also have educational outcomes. So we're going to look specifically at math and reading achievement, and then fraction of special needs, and also daily attendance. Yeah?
A clarifying question. Could you show us the pictures of the water is that like, that's not the lead, right? Like that's just dirty water, right? So like if I was a household that had lead pipes and there was a household down the block that didn't have lead pipes, we would both be getting that dirty water.
Yeah. So
Is there some correlation between lead pipes and any other important?
So to be honest, I don't think we totally know. So like certainly the water itself was corrosive and untreated. I do think it would look different sort of at the treatment center than it would look at even in someone who had copper pipes or galvanized steel pipes, which are less risky. Like I think it's possible that water was kind of gnarly as well. So I think it's likely that everybody in Flint had some degree of kind of bad looking water. I don't think we totally know, like, would we expect it to be really different in like a lead child's house versus a not lead child's house?
I'm thinking like within Flint, is there any mechanism for feeling marginalized for the households that did have the lead pipes? Like, did they recognize that they were somehow different than?
Yeah. No, that's a good point. I mean, there were some. Well, this all happened sort of later, but at some point there were water tests, so people, might have a sense of how much lead was in their water. The issue is that these are really noisy, so I don't think it's like very accurate. I don't think that we expect the water to look different in a lead house versus a non-lead house, but I just don't have a concrete answer. Yeah. So I guess the three kinds of pipes that people had in Flint were lead, copper, and galvanized steel. Copper is sort of the gold standard now. It would be like the safest in terms of lead exposure. Galvanized steel we don't really use anymore, and it sort of breaks down on the inside. And I think galvanized steel, for example, might have kind of less lead risk than the lead pipes themselves, but they might actually have sort of like gnarlier water. Like galvanized steel sort of breaks down, but lead also breaks down. So I'm not an environmental engineer. I'm not totally sure.
But I think Eric's key thing was, is there any way people might know what type of pipe that they had?
Right.
And I think it's hard to know, like unless, because it's the service line coming in from as opposed to stuff that you can look under your sink.
That's right. So yeah, to Eric's point, like people certainly didn't directly know what kind of pipes they had at the time that sort of we're studying. Now that they've all been replaced, in retrospect, many do know, or most do know. But that's not sort of going to be within the time frame of our data.
Yeah.
Could they have known from some indirect pathway of like,
Looking at
my water was worse than my next door neighbor's water? I don't think so, but I'm not 100% sure.
Sam?
Yeah.
How frequently does the service line material vary? Like, does it tend to be like a block is all going to have the same type of service line, or could it be the three houses in a row? One is lead, one is galvanized steel, one is copper.
So on a neighborhood level, there is a lot of variation explained. So we use census block fixed effects in some of our strategies, and basically there is many cases where, and I'll show you a map later, but there's many cases where like three houses in a row have different pipe material. Basically, I would think about it as there's some areas of town that are new enough where basically all of the pipes are copper. And then in the areas of town where they're old enough to potentially have lead, then it's pretty varied. And again, we're going to focus just on kids above the age of 5. So here, I'm going to use math achievement as like a running example for all of the figures, but I'll show results for sort of all 4 of our outcomes. But this is just the secular trend in math achievement. So we start, good data starts in 2007, and this is all the way up to right before what we're calling sort of the beginning of the water crisis, the treatment time in 2014. And so you can see basically there's a precipitous drop in math achievement. But again, we don't totally know. These are striking, but they're only observational. So they may result from year-to-year changes in different things, tests, economic conditions, for example. So anyways, we want to, I don't need to explain this to this group, but we need a causal inference strategy to sort of really get to the heart of this. Yeah?
I know you said you're not a biologist, but how is it known how quickly lead will impact people's cognition?
Yeah, I think there's actually, so there is some evidence, like basically from like animal models, like they actually give monkeys lead and look at that. I think it's not sort of immediate, like for example, like the next day, but I think it's like within the kind of the next 6 months, is my understanding. But again, I'm not an expert in this. I do think most of our sort of quasi-experimental studies of lead are looking at childhood lead exposure and then sort of like middle school or higher sort of outcomes. So there's a pretty big lag between sort of like, at least in our sort of like economics, education, sociology literature of lead exposure and then the outcome.
So what is that clock? Or like, what is math achievement when? Like, is that the average, like in 2013, are we looking at the average scores of all tests given in 2013? Or is it for a cohort of 5-year-olds in 2013 when they took their tests some number of years later?
This is for like all tests given in 2013. So yeah, this is going to be, you know, just standard deviation units of the statewide distribution on the y-axis. So here is just saying that, you know, so basically every dot here, only like the sample is changing slightly. It's just like one cohort is sliding through. So we're basically seeing that all of the kids in sort of grades 3 through 8 in Flint public schools, their average score in sort of just before the water crisis. Michigan actually had spring tests then, and they happened, you know, like a month before the water crisis occurred. Or sorry, they had fall tests then. So basically, there's actually a longer gap between this dot and this dot than it's more of a 1.5-year gap because Michigan switched from having fall tests to having spring tests basically around when the water crisis was happening. So there's about a 1.5-year gap here rather than just a year, and it probably should visualize that. But so this is saying that in 2014, the sort of like the average Flint student had performed sort of 0.5 standard deviations below the mean, and this is saying now it's more like negative 0.65.
And they didn't know about it, like the story about the crisis.
Yeah, the crisis
years
wouldn't
just-
have broken until around here.
It's like, so it's not because, all the high scoring people left.
Right, and we actually have some robustness checks to talk about like out-migration later on. So we have to construct a counterfactual using a control group, just like in the school shootings case. In Flint, this actually turned out to be quite challenging. Flint's a very unique city within Michigan. It's large, but not huge, so it's not Detroit. It's got a high fraction black and high fraction students who are economically disadvantaged. And basically, we couldn't find a good district that met the common trends assumption, or a set of districts with equal weights that met the common trends assumption. So, you know, the traditional difference in difference inference wasn't really available to us. So here we can kind of play a game where we guess where is Flint in this distribution. On the y-axis here, we have fraction black of a district. On the x-axis, we have fraction economically disadvantaged. And each dot is, you know, a district. You know, the size corresponds to how big it is. We can all see Detroit up here. Flint is right there. So Flint's quite large for Michigan, and it's an outlier in terms of these two variables. So what do we do when common trends fails? Here, synthetic control is kind of the answer that we turn to. It was introduced by this Abadi, Diamond, and Heinmuller paper in 2010. I'll actually flag that, you know, they did a great job starting off this literature, and I think actually there was an Abadi paper even earlier. But in practice, synthetic control applications today, I think, depart quite substantially from this original sort of formulation, and I'll discuss specifically what we do. So Susan Athey and Hideo Imbin say that synthetic control is arguably the most important innovation in the policy evaluation literature in the last 15 years. The general idea is that we generate a synthetic Flint as a counterfactual. So we basically, rather than looking at sort of one or a set of control districts with equal weights, we're going to use a weighted average of control districts that do match Flint's trends. So we might be able to expand the common trend space by basically taking a weighted average rather than sort of just a regular average. So the weights, in our case, have to add up to 1. There are some synthetic control applications that vary from this. But so, for example, synthetic Flint could be 0.5 of Lansing's outcomes plus 0.3 of Kalamazoo's outcomes plus 0.17 of Detroit's outcomes. And that would be our synthetic Flint that was supposed to recreate basically the post-trends of our outcome variables for Flint. So synthetic control is a generalization of difference in differences. It brings difference in differences into the era of big data. It does this by computationally automating the counterfactual selection process. I think there are pros and cons to this. In one sense, it removes researchers' degrees of freedom. Like it means that there's not this thing happening kind of away from the paper where you're checking common trends before you even start the study. I think it does add in new complications, and we can talk about those in the Q&A. But basically, in our case, there's an algorithm that finds the weighted average of control units that best approximates the treated unit. And in doing so, you're able to greatly expand the space of common trends available. So even though there wasn't a single or a set of districts that, on average, matched Flint, we're able to get pretty good fit using synthetic control. So there are many versions of synthetic control. I would say the literature is very much still in its adolescence. Our synthetic control is unique. We match only on trends, not on levels. So this is sometimes referred to as demeaned or intercept shift synthetic control. And this is actually what you already do in difference and differences. So this is, basically our estimator can be expressed as a weighted difference and differences. And it closely resembles basically these two proposals that came out, one from a Berkeley group and one from a Stanford group at about the same time. One thing that is unique about our synthetic control, and there are starting to be more people who do this, but we fit all 4 outcomes simultaneously. So we only have one synthetic flint for all 4 of our different outcomes. We thought it was conceptually unsatisfying to have many synthetic flints that had different weights. But we also have done robustness checks to sort of make sure this doesn't change our results. I think there's this weird way that synthetic control is a little bit opaque. It's a little bit computational, and I think sometimes it can have, people claim that it works, and it just seems like magic. And I think that the intuition can be explained very well visually. So we're going to take a little bit of a departure from the talk proper to talk about what's going on with synthetic control. A brief graphical guide. So this is just fake data. This is 4 districts. We have Lansing, we have Flint, we have Kalamazoo, and we have Detroit. And we're just, for simplicity of the example, we're observing them in 3 periods. So we observe in 2001, in 2007, and 2013. Notice these are all in the pre-treatment period. So we're trying to find which one is going to best or how we're going to sort of combine Lansing, Kalamazoo, and Detroit to sort of approximate our post-Flint outcome. So all of the fitting of the synthetic control happens in the pre-treatment period. So the first thing we're going to do is just slide them all down. So this is the original figure. And remember I mentioned we use demeaned intercept synthetic control. So we're just going to slide all of these lines down to the same 2001 variable, or 2001 level. So we're demeaning them. We're only looking at the trends, not the levels. I say demeaned. In practice, we actually use the mean. In this case, I'm going to use the first one, but it's the same thing in terms of degrees of freedom. So basically, I took those lines and I just slid them all down to the bottom. And now I'm just going to blow this image up bigger. So now we've sort of shifted all of our intercepts down to the same sort of starting point in 2001, and we're just looking at the trends in the districts over time. Right off the bat, we can see that none of the 3 sort of control districts individually have a common trend with Flint, right? At first, maybe it seems like Lansing could, but then Lansing and Flint's trends depart when we move from 2007 to 2013. So one thing that I want to highlight is that now that we've sort of simplified the data here, now that we've demeaned, we've intercept shifted it, and we only have 2 data points that we're really matching on here, right? We're only matching on 2007 and 2013. There's another way that we can express the same plot that actually has a lot more intuition about what's going on in terms of synthetic control. So rather than having outcome on the y-axis, and having year on the x-axis, because we only have 2 years, we can just say 2013 outcome on the y-axis and 2007 outcome on the x-axis. So we can just literally transfer this data over from the left-hand plot to the right-hand plot. So let's focus on Flint first. So 2007 outcome, 2. 2013 outcome, 2. So 2007 outcome, 2. 2013 outcome, 2. Flint's going to end up right there. Now we can do it with Lansing. Lansing, 2007 outcome is going to end up, so we're transporting this data point over to this, and we're transporting this data point over there. So it's going to be 2, 1. Lansing's going to end up right there. And basically, we're able to transfer all the data over. We can do the same thing with Kalamazoo. Kalamazoo, 2007, 2013. So 1, 3, 1, 3. Kalamazoo is going to end up right there. So all of the same data is being preserved. We're just moving it to a new visualization. And this visualization is going to be more sort of useful in understanding what's going on with synthetic control. So we're just going to blow that one up. So here we have Kalamazoo, Lansing, and Flint. And we can see right now, basically, the 2007 and 2013 outcome in this simplified example contain all of the information about the pre-treatment trends of each of these districts. So we can see basically that they don't have a common pre-trend just by the fact that they're not on top of each other in this covariate space. So what if we're able to take an average of Kalamazoo and Lansing? Well, if we take an average Kalamazoo and Lansing, we're going to take an average of 1 and 2, and we're going to take an average of 3 and 1. We're going to end up right in the middle, graphically, between them. So this is a 50-50 weighted average. So if we just made our control district both Kalamazoo and Lansing, and we weight them equally. So that's actually a little closer to Flint in terms of trends, but it's still not perfect. But we don't have to take just a 50-50 weighted average. This is the whole intuition behind synthetic control. We can take a 75-25 average. We can take a 25-75 average, and we can actually, just by toggling the weights of this weighted average, recover anything on this line between Lansing and Kalamazoo, just using positive weights. So basically, with when we're using synthetic control, if Kalamazoo and Lansing are sort of our only two control districts, then this area, this line in between them, is our options in terms of recovering common trends. So we can connect those two lines. But remember, we have one more district. We have Detroit. So what if we add Detroit back on here? Using the same thing, if we take a weighted average of Lansing and Detroit, we can end up anywhere on the line between Lansing and Detroit. So that's giving us sort of more common trends. And we can also take weighted averages of Kalamazoo and Detroit, and we can end up anywhere on the line between those two. And if we're willing to take weighted averages of all three, Kalamazoo, Lansing, and Detroit, then we can end up anywhere within this sort of triangle that's being drawn here, which is in, so this is called the convex hull. So this is basic, and now because Flint is within the convex hull of our control units, we're actually going to be able to match the pre-trends perfectly. So again, this is a very simplified example. One thing I want to flag is, imagine that we had more pre-treatment years. So rather than just 2 where there's variation, we had 3. Well, now we would be in a 3-dimensional space. So we can imagine sort of a z-axis going sort of off backwards towards the chalkboard. And the convex hull would not be sort of 2D, it would be 3D. And if we have sort of 5 or 10 pre-treatment years that we're trying to match on, well, all of a sudden now the convex hull is like an n-dimensional object. We can't visualize it, but all of the math sort of holds over. And again, the convex hull of these 3 data points is a triangle. But if we had a 4th control district, well, then it would be a quadrilateral, and so on. So you can imagine kind of, when we have, in our case, about 10 pretreatment periods and, about 50 control units, like what the convex hull might look like. So in this case, the solution is 0.5 Lansing plus 0.33 Kalamazoo plus 0.17 Detroit. That's what gives you Flint, the common trends or the Flint's trend in the pretreatment period. So we knew there was a solution because Flint is within the convex hull, and that just happens to be the solution. Remember, this is just kind of made up. We'll find the real solution for Flint in a sec. One thing I wanted to flag is that Flint's not always, especially as the convex hull becomes more dimensions. You're typically not going to have perfect matching in the pretreatment period. So Flint's actually not going to be in the convex hull, it's going to be near the convex hull. And so here but we're always going to do better with synthetic control, or like we're going to do weakly better with synthetic control than we will do with just kind of classic difference in differences. You can also allow for extrapolation outside the convex hull. Some of these synthetic control methods allow for this. Basically, machine learning is helpful here because you allow basically for negative weights, and that lets you leave the convex hull. But if you don't have some sort of regularization, then basically the whole your variable space is available. So you basically need to bound your extrapolation outside of the convex hull sometimes. So one strategy is to use elastic net. But in Flint's case, basically we don't have enough pretreatment data for this to be a useful strategy. So we're just using the simple positive weights weighted average synthetic control. Okay, so how are we going to implement our synthetic control? The first thing we're going to do is select potential control units to minimize apples to oranges comparisons. Then we're going to use this algorithm to identify the optimal control weights. And then we're going to construct synthetic Flint, and we're going to take the difference between actual Flint's post-treatment outcomes and synthetic Flint's post-treatment outcomes, and we're going to estimate the causal effect. So going back to this graph where we have fraction black and fraction economically disadvantaged, basically we're going to restrict the potential control units to the districts that have either a very high fraction black or a very high fraction economically disadvantaged. So basically we drew a line here at the 90th percentile of each of those distributions, and we're just going to take all of these blue units, all of these units that are at least in the sort of top 10 percentiles of one of those variables, and we're going to, so there's 54 control districts, and that's going to be our donor districts. That's going to be our potential synthetic control districts. So then we actually fit the synthetic control model, and Flint becomes a weighted average of 10 districts, and those which I've put in purple here. And we can, after the talk, we can talk about which specific districts there were if you'd like.
Were you matching just on pretreatment trends?
Just on pretreatment trends, no use of covariates here. You can use covariates when you have a very limited panel length. Sometimes it makes things more difficult. I think the consensus, though, is that you probably shouldn't use covariates in the way that a body in 2010 proposed, but there are different ways to use them. But yeah, again, we're just matching on trends here.
I thought Abadi in his recent papers doubled down on covariates.
I don't, so yeah, I'm not sure the paper actually. So basically, now that we have our synthetic control, we can add on to this original blue line, basically what synthetic Flint would have experienced, this weighted average of those 10 districts. And we see that in the case of math, there's a pretty precipitous difference. So the difference between these two lines is sort of the causal effects in the synthetic control world. Rather than graphing two lines, we can do something called a gap plot, where instead of plotting both these lines, we're just plotting the difference. So here's that gap plot. So the y-axis, rather than being math achievement, is the difference in math achievement between Flint and synthetic Flint. And in the pre-treatment period, you expect it to be quite close to 0. That's just like sort of as a measure of fit. How well are you able to approximate the pre-treatment trends? And then in the post-period, any difference is considered to be the causal effect. And here you can see a causal effect of about negative 0.14 standard deviations. Yeah.
So Sam, even the synthetic controls see a big, decline following 2014. Do you know what that was? Like, did they change the test? Like, did the test?
They did change the test, and I do think it's possible.
that the
So
test
when they
was-
changed the test time, they also changed the test. I don't like so it could be something about like the way that the test is capturing variation in this end of the distribution, because this is like we're in like the really pretty negative ends of the distribution. On average, like Flint is one of the sort of the lower performing districts in the state. But I don't really know sort of what is causing this red decrease.
When I saw this chart, I sort of thought, like, at least as it's described in your paper, like, Governor Snyder is like a scapegoat. And I wonder if, like, you're a black child in Michigan, Governor Snyder is also your governor. So maybe you're like, you have some stigma or you have some, like, fear that you also, I don't know.
Yeah, so
But,
so
like,
maybe, there's a story to tell here where there's like actually spillovers of the Flint water crisis onto like other children in the state of Michigan who are not living in Flint, who the water has not been contaminated, but sort of feel like an indirect cost of basically this Governor Snyder or the the Flint city government, Flint state government, or the Michigan state government, kind of denying the existence of a crisis. I think that's reasonable. If that's true, then basically this would be a lower bound of the,
attenuating.
of the effects.
You matched on trend, but you have overlap on what looks like an absolute scale. Are those lines shifted or aligned, or did you just end up nailing it in terms of the overall scale when you matched on trend?
So you basically, in this case, we matched on trends, and then I basically just like added the mean of Flint back into the synthetic control.
Oh, so you realigned the synthetic control line to, okay.
There.
Just a quick follow-up question. So if there was a change in the test in 2015, do you observe a change in the test in any of your pre-data, or is that all one test?
I think that there might be a different test around here, but there's, I think, like, at least the sort of the 5 years before the, like, sort of the 2014 to 2015, where they changed the test timing and they changed the name of the test. I think it was the same pre-test, yeah. So again, here, pre-treatment period, the gap plot's telling us the fit, and the post-treatment is telling us the basically causal effect estimate. One thing that's nice about these sort of synthetic control estimates, so the confidence intervals are estimated empirically, and they quantify two kinds of uncertainty, and this is like a kind of uncertainty that's basically absent from the just difference in difference literature. So the first is uncertainty in what's our control going to be, what are these weights, basically which districts comprise synthetic Flint. And then there's also sort of the classic uncertainty, like the sampling variance of like whether the synthetic Flint and actual Flint are statistically significantly different. So here is the same plot for special needs. We see, around 0 in the pre-treatment period and then an increase in the post-period, but we don't see any effects on reading achievement or attendance.
Sorry, Sam. Are these the Abbey, Diamond, and Pioneer confidence intervals?
No. So these are from. There's the Feller, Rothstein, and Ben Michael paper. It was in Journal of American Statistical Association. This is their like jackknife confidence intervals. So people have moved away from the initial so initially the way they would generate confidence intervals for synthetic control was to be like, well, let's imagine that all the other units were treated. Like, so it's kind of a randomization inference. But I think there's a lot of questions about whether randomization inference was sort of valid in this case. Like is it a good assumption to think that that sort of we can treat which district was treated or which unit was treated as if it was random? So now people use things like kind of jackknife style procedures or conformal inference standard errors. At least that's what I've seen.
And the jackknife is you refit, you exclude one donor unit at a time and refit.
That's right. Yeah.
Which is weird because it's sparse, so you're going to get the exact same estimate if you exclude any of the donor units that weren't picked up in your original estimate.
That's right. You also exclude pretreatment years, though. So it's a jackknife over sort of both units and pretreatment years.
Okay, so you wiggle things around and then you adjust how much they wiggle to get your standard errors.
That's right. So in terms of, oh yeah, go ahead, Tom.
Sorry, Sam. But it just so the demeaning, in this case, like if the change in the test meant that like all of the schools that were scoring at the lower end suddenly like started doing worse on relative to everybody else in the state, the demeaning would sort of make that, would add to bias, like the including the level in the matching is at least trying to take part of that, right? That it's trying to say, okay, I'm going to try to find people that are matching not just on the trend, but are also matching to some extent on the level. But if you demean everybody, you're only worrying about the trend and not the level. And in some applications that might matter, but in this case, like if there were some very different trend, depending on what your prior mean achievement was.
Right. So yeah, so this red dot here, like the synthetic control, is just identified off of the change in like the synthetic control, like after demeaning sort of the synthetic control units, the change from sort of like pre to post. And so that's right. Like I think, so basically we can't fit this model without demeaning. Like Flint is just in such a sparse area of the achievement distribution that there's just like not units to do it. But that's right. So like if there was a change in test that actually sort of distorted different regions of the distribution, and that distortion sort of differentially affected Flint compared to sort of the control units because maybe they were at different levels of the distribution, then that could bias our estimates. I think that's right.
Or like even if you just said, okay, we'll show this where it's just matching purely on the trend, and then maybe the other extreme is suppose you match just based on 2014 score. Mm-hmm. Like so you found. You said, all right, I'm going to find districts that had similar demographics and, similar 2014 score, and then.
Yeah, so this sort of raises an interesting point, which is, I guess, going forward a little bit. So something's very funny about synthetic control is that these two things often work in different directions. So the uncertainty about which districts comprise synthetic Flint and then whether sort of synthetic, like basically whether synthetic Flint and actual Flint are statistically different, which has to do with like pre-treatment fit. Basically, so so Tom's suggestion is like, well, what if we just fit it on one data point sort of before, rather than on the pre-treatment trend? What if we just like fit it on 2014? Something that's weird is that you could get really good fit. Like the shorter the panel here, right? Like the better fit you're able to get sort of for a given number of control districts. But then the better fit you have, the more uncertainty in which district should actually be in your synthetic control, because there's basically more ways to more linear combinations of different districts that can recover the pre-trend. So currently there's this interesting battle between these two things where there's almost like a ratio between how many pre-treatment units you have, pre-treatment periods you have, and how many control units. If your control units goes to infinity, well then basically there's infinite number of linear combinations of those control units that can recover the pre-treatment trend. And so this sort of the number 1, which districts comprise synthetic flint, goes way up. And then if your pre-treatment period, if your number of pre-treatment periods goes to infinity, but you keep a constant number of control districts, well then you're not going to get very good fit, and so number 2 goes way up, like whether the synthetic flint and actual flint are statistically different.
Yeah, so all I'm saying is, in this case, I mean, one possibility is that you have a special case where the post-treatment trend may have been very different based on the pre-treatment level, just because of the change in the test. Like,
Yeah.
lower scoring schools were suddenly doing a lot worse on this test. It's a harder test.
I think that's right. No, I'll have to look at sort of like,
And so I'm not making a general point about about different types
Right,
of
right.
synthetic control. It's just in this case, like the way to answer the question, was it just that that there was a different post-treatment trend based on pre-treatment level? Like, one way to answer it would be, well, let's just match on pre-treatment level. And
So yeah, I mean, I don't think I've directly. So I think we can't match on pre-treatment level, kind of for this reason. Like, this doesn't totally show it to you, but like, Flint is in a unique like area of distribution in terms of like to fit a synthetic control, you kind of need like multiple things in its general like covariate space. And Flint just doesn't have other districts or enough other districts in its covariate space in terms of outcome level to like match on level. The one thing we've checked is like you don't see a similar decline in Detroit, and Detroit and Flint have basically the same pre-treatment test scores. So that's encouraging, but I do think there's more that I could do to sort of like make sure that this change in test is not kind of the thing driving the result. Yeah.
I think part of what's inside Tom's mind is that there's a correlation between level and the sort of the effect of the change in the test.
Right.
Yeah. And that I suspect that's probably true. But like if you have in your pre-treatment data another event where the test changed, right? You could match on sort of response to a change in the test.
Yeah.
So like it's not just about the identifying assumption isn't that the pre-trends are similar. The identifying assumption is that the trends
would have been the same.
after the treatment would have been the same. And so maybe it's the case that if you had that earlier event where a test changed, you could use that.
Yeah.
Although this is a weird test, like usually the change in the test, you don't see a big reshuffling like this, like but here, like wow, like that's just weird to see that.
So I guess I'm not convinced necessarily that this is like go ahead.
Just on that graph that you were on here, can you just say a little bit more about restricting the sample?
Yeah, so that
control to those.
I mean, there's sort of like so as robustus, we're going to try different cut points basically in a smaller set of donor districts. But again, so this gets to what I was saying to Tom that wasn't necessarily directly related to the thing that he was saying. But there's this sweet spot between the number of pre-treatment periods you have and the number of potential control units that you use. And if you have too many periods for your number of control units, then your standard errors go way up. If you have too many control units for a set number of pre-treatment periods, then your standard errors go way up. So basically, there is sort of just like an empirical sweet spot of like you have to kind of pick, you have to make sure those things are in tension or like sort of aligned with each other. Here though, I mean, there's also this like, basically the advice I was given was like, don't match on any district that if it ended up in the Flint control, synthetic control, that you'd be like, I don't believe that. So like, so sort of just like, in that if you can't use all of your control units, given the number of pre-treatment periods you have, then basically just like use some kind of common sense test to sort of restrict the potential donor pool. So talking about the change in test, like, I guess I'm not convinced, and maybe this is something better to circle back to at the end. But I definitely, so I do think that there could be a way in which, the red line is differentially affected by a change in test compared to the blue line, with the blue line being Flint and the red line being the synthetic control. But I'm definitely not convinced that that necessarily this was a change in the test.
Yeah. Nor am I. I'm just saying it's a possibility. So,
couldn't you just plot all of your districts that are on a low end test distribution over time and just as a spaghetti plot of all the districts? Because if there's a hypothesis that there's a test, you'd expect it to be shared across district and you
Totally.
can see everything then.
Yeah, no, so like early on, this project has like spanned many, many years. Early on, we have done that, and I don't so we don't have evidence, like we don't think that there was big change in test effects, but I'm just like not that well acquainted with those results like right now. Okay, so in terms of robustness, what do? We run the model a lot of different ways. So one way is sort of to control for selective attrition. So like the results I've showed you were basically they had a district assignment. So we're using geographic districts, so it's based on where people live, not necessarily where they attend school, but this should sort of map onto exposure to the crisis in many ways. We also don't use any of the bordering districts to Flint geographically in our synthetic control or like in our sample. But so the way we've assigned it is basically like in 2015, it's the kids who live in that geographic district in 2015. But we actually can follow the kids anywhere they go in Michigan. So we also can define a student's district not as time varying, but as something that is just fixed statically pre-treatment. And so basically we can control for selective attrition in that way. Actually, the attrition is not very high. It's less than you would think. Flint is genuinely declining, but didn't decline that much, like didn't decline any additionally, actually even less pre-post to the water crisis. But basically we can make a definition of districts that is robust to people leaving as long as they stay in state. Very, very many of them stay in state. Actually, the most people who leave Flint stay in the county. Like the vast majority. So anyways, we can sort of like sort out the selective attrition problem. It doesn't seem to be an issue. We can also fit on a smaller set of control districts. So rather than the 54 in the top sort of 10% of those variables, we can do the 27 in the top 5 percentiles. And then we also can fit, rather than doing that joint sort of one synthetic Flint for each outcome, we can fit it individually. So like we can have different synthetic Flints for each outcome, and we can also maybe do smaller combinations of the outcomes. And basically all of these give us the same results. Sometimes there's, like in some of the models, there's negative effects on reading that emerge, but not systematically, maybe in about a third of these robustness checks. So we're not going to lean on those.
Sorry, did you say your original analysis, you fit a single synthetic Flint matching on all of the different outcomes at once?
That's right.
So, which means that you had multiple time series. What do you mean all of the outcomes?
Yeah. So basically, yeah. Time here is that's right. So you're just basically like stacking all the outcomes together. So math achievement, reading achievement, attendance, and special needs. So basically, we're finding one set of weights that simultaneously minimizes basically like the L2 distance.
And you standardize everything first.
That's right.
What package are you using?
This is the Feller, Rothstein, and yeah.
Okay.
Okay, so overall effects of the Flint water crisis. So we find substantial negative effects of the Flint water crisis. So it's a 0.14 standard deviation decrease in math achievement, 9% increase in special needs, more mixed results involving reading achievement, but still on the negative end when we find them. So this is sort of medium effects in the educational literature, but it's very large actually if you look for negative effects. I mean, a lot of this review, this Craft Ed Researcher one, looked at RCTs and things like that, and I think we hope those have positive effects. So it's kind of rare to find something that sort of hurts so badly. So turning quickly to the other part of my analysis, the question is, can we better understand the role that lead played in these observed effects? So this is circling back to the beginning of my talk when I talked about the various mechanisms that are identified in the between district analysis. So we're transitioning from this between district analysis to this within Flint analysis. So quickly about this new data we're adding in. So we have Flint property level service line data. Basically it says copper versus lead or galvanized steel. This was collected after the water crisis, like well after the water crisis, during pipe replacement. This is a very expensive thing that happened. Part of the sort of like all of the media attention and the funding that came into Flint after the water crisis was what led for this to happen. So as of when we did our analysis, 92% of residences had been observed, and if they had lead pipes replaced or galvanized steel, and 40% of Flint had lead pipes. So here's a map of Flint, and this is just sort of showing you the distribution of lead pipes. So we match each student's education record to their house's pipe material using their home address. This was quite difficult, and I'm happy to talk about this after in the sort of the debrief. But eventually the Michigan Attorney General, I believe, had to sign a piece of paper, and that took a long time. So I've showed you this plot many times already. This is the math achievement, and we can look at how sort of it changes over time observationally, and we can compare that to our synthetic Flint. What this new data allows us to do is to break this line out into two subgroups, to a copper and a lead subgroup. And basically, so we have lead is red here and copper is black, and we just don't see really meaningful differences observationally in their trends pre-post. And we actually run sort of the modern difference in difference methods, the ones that are robust to sort of heterogeneous effects over time or across units. And basically we get null results again, and pretty precise null results. So things that are not like basically we don't see any systematic differences between children who had lived in homes with lead pipes and children who had copper pipes over time in Flint. So kind of synthesizing all of this together, empirically lead pipes explain very little of the observed math effects. How much of these should we expect from lead? We can kind of turn back to the literature. The answer is actually not a lot. So at the beginning, I said our best estimate, which might be sort of noisy, is that there was a lot of variation in lead exposure in Flint, but on average the increase was 0.5 micrograms per deciliter. And the best evidence, from these two papers, one's Azer 2018 and then Rubin 2017, is that this amount of a lead increase should correspond to about a 0.01 to a 0.015 standard deviation effect on sort of cognitive tests. And here, if we compare, so one uses math achievement, one uses like a kind of classic intelligence test. But here we can see that these are about an order of magnitude different. So basically, hypothetically, we don't think the lead could have explained such big negative effects. So theoretically, it explains very little of the math effects. But one thing I want to flag is this doesn't mean that lead didn't affect the children in Flint. I think there's something really important about our sample characteristics here, and that we're studying kids who were on average older when the Flint water crisis happened. And I think that there's kind of these dual mechanisms at work potentially here. And so we have these social mechanisms, which I argue might increase with age, but that's sort of speculative. And we have these health mechanisms, which we know definitely decrease with age in terms of lead. And so why would the social mechanisms increase with age? It might just be that if you're 3, life before and after the Flint water crisis doesn't look that different for you. Whereas if you're 10 and you're in school and people are skipping school or people are upset, then you actually sort of internalize a lot of the stress around you. So I'm just arguing that we actually might be right here, right? Where the health mechanisms are kind of quite small compared to the overall social mechanisms. Interpretation. So the social effects of the Flint water crisis were large compared to the health effects, at least for school-age children. But this actually means that we currently substantially underestimate the cost of the Flint water crisis. So existing estimates of the crisis, the social costs, the societal costs, they only use sort of the increases in lead, not the overall effects. And so the existing ones range between $50 and $400 million. But you actually were seeing that the social effects, at least for some of the population affected, were quite large compared to the direct lead effects. And so the true costs are actually going to be a lot bigger, and the social component's a big part of the story. So to sort of revise our theoretical model here, we have structural forces, failure of public institutions, environmental health exposures, child development. But now we have this new line, which is there's a way in which maybe these failure of public institutions is affecting child development sort of more directly, not through the lead in and of itself. So it plays an important role. And again, this is just speculative. We don't really know. We can separate out the lead effects, but we don't totally know what went on. But it could be things like stigma, marginalization, social unrest. So I think synthetic control provides new avenues for estimating causal effects. Useful in sociology, that's where I come from. We're interested often in studying specific historical events in context. And so it's, you don't have a lot of, you can't combine many events together to, estimate differences, for example. So there was a substantial negative effect of the Flint water crisis on affected children. Large effects, large social effects in addition to whatever health effects, if you consider the fact that they're negative. And I think it's just not sufficient to treat the crisis merely as a public health crisis. It's more than that. Hopefully this research draws attention to these water crises and they produce inequality across place. And there's quite cheap preventative measures. And so an example of that, the Flint water switch was intended to save $5 million. And now updated social costs range from hundreds of millions to billions of dollars. So basically, these things can be really costly. I quickly wanted to talk about, Tom asked, with an eye towards COVID to talk about Flint. So I tapped Jen Beam Dowd, who's a demographer at Oxford, and she's more of an expert on the effects of COVID on everyone, but on children too. So there's a couple quick similarities or differences that I wanted to draw between Flint and COVID. So I think the biggest similarity here is that they're both likely going to cause twin causal processes. So there's this individual level biological shock. So it could be lead exposure in the case of Flint, but for COVID, it's contracting COVID, right? Getting sick. And then there's these community level social responses. So schools get shut down in the case of COVID. There's community in crisis for Flint. And I think there's going to be likely heterogeneity of each of these treatments by age that sort of probably works in different directions. To think about what might matter for the biological shock, we want to think about key sort of developmental periods biologically. And then for the community level response, we might want to think about whose lives were most affected sort of pre-post, like whose circumstances really changed. In terms of differences, I think that the individual level biological shock has much more treatment variation in the Flint case than Flint for COVID. So it was close to 0.5, which how many kids were exposed to lead pipes, for example. But I think to show this with COVID, on the y-axis here we have basically the fraction of kids or fraction of people in the age group that were tested positive for antibodies to COVID that were not from the vaccine, so that sort of indicated a previous infection. And so you can see for people 5 to 11, 12 to 17, like in the classic kid age, the prevalence is quite high in the US. This was like 75%-ish. And this was in February of 2022. And so I think now we'd expect these to be even higher. So almost everybody has gotten COVID, is what I'm trying to say. But in Flint, not everybody was exposed to the lead or exposed to the same amount of lead. But I do think we have more heterogeneity in responses to COVID. So some people, take COVID quite mildly, and other people have long COVID. There's myocardia. There's multiple inflammatory syndrome in children. And so, there's these things that might sort of, whereas sort of a given amount of lead being ingested into a person's body, I think at least as a fraction of their BMI is going to be quite similar on their outcome. So there's maybe more homogeneity there. And then I think the age slope of the individual level biological shock is negative for lead, but it's actually largely positive for COVID. So lead affects us less as we age, and I think COVID affects us more as we age, even among children. So here's COVID deaths. This is just raw deaths, so it's not comparing it to sort of other risk factors or per X thousand kids. But you can see they largely increase over time after sort of this infant period. And there's just much higher mortality in early life than there is later on. And so if you look at basically like cause of death factors, then this middle period, like basically being over 10, COVID is a more substantial sort of portion of total deaths in the US for kids, over 10 than under 10. And anyway, so I think that we think that COVID probably affects you more as you get older, even sort of within the under 18 age range. And that is all I have. I think maybe the last thing I'd say about the differences is that Flint was very much like one community being marginalized within a state, where COVID is sort of happening to everybody somewhat differently, but maybe there's more of a vibe of we're all in this together. Maybe it could be meaningfully different to be in Flint and feel like you're getting the raw end of the deal, but other people aren't. And that is all I have.
Do we have time for one more question?
Yeah, I think so.
So I want to ask, if I recall correctly, I'm from Michigan originally, but not from Flint. There were other characters in the story who did testing work that wasn't sanctioned by government. There's a Virginia Tech.
Mark Edwards, yeah.
Yeah. As you said, he must have been testing at people's homes. Do you have any sense of the scope of those efforts that, to someone's previous point, they might have identified, people might have known because of these other sort of non-sanctioned efforts that nonetheless were probably high quality?
Yeah, I mean, so there is some data out there, both from, sort of like the Edwards group, but also just from there's sort of general testing that happens from the state of Michigan. We've tried to use the water test data to some extent in our analyses. So in an appendix, we look at how lead pipes sort of predict the water test. And they do sort of highly statistically significantly. I think, there's multiple, I don't remember the exact numbers, but basically if you have lead pipes, you have much higher lead tests than those who don't. But the lead and water tests are just very, very, very noisy. And this is a really hard thing with lead. because it's also very noisy to measure in the blood. But with the water, basically, it matters how long the water's been sitting, sort of how long you let the water run before you test it. So you can imagine like some of the water in your pipes is like actually in your house, and basically it's much less likely for somebody to have lead pipes within their house that are visible. Those have like largely been changed out. And then there's some of the water that's sitting in the service line, and that basically how long it sits in the service line and whether you get that water versus the water that's sort of ahead of it or after it really matters in sort of the quality of the test. So just a few feet difference in which water, like what water you're getting, can really change like the test result. And so I think basically there's a limitation to how much we can use that data. But basically what they do is that any positive test is like a really bad sign, but we have basically a lot of false negatives.
Is lead the only thing in the water that has biological effects? We know that.
I think the only other primary thing was Legionnaire's disease, which is like a bacterial infection, but it just primarily affects adults. So I don't think, I mean, like maybe there could be an effect that could be baked into like the between district effect. For example, like if my parent gets sick, maybe that affects me in school. But I don't think we think that was affecting the children.
But so I could just drink if I had a copper line, I could just drink it in the water.
I think so. I mean, like I guess I don't. That's a good question.
Because that would then explain it. I mean, there could still be a health effect that everyone got because it wasn't that.
Totally. That's right. That's a good question. I think that there's nothing else specific that I've read that sort of was a problem with the water. I do think a lot of people stop drinking the water. So there's a way in which like the results from this, like the treatment effects of lead, even on the younger kids in Flint might be much lower than in like sort of DC or Newark, somewhere where like basically it was a very gradual change in the water regulation and there wasn't sort of these big color and odor changes. So in some sense, the color and odor changes might have lessened the lead treatment effect just because less people were drinking the water. Sebastian.
So I was wondering, you said at the beginning that you did this talk as well in Flint, and I was wondering what was the sort of takeaway. I mean, the talk is called Learning from Flint. What was sort of the reaction there or the takeaway?
Yeah.
And another quick question, choose which one you're more interested in, is you hypothesize, you suggest that it's the social mechanisms that become more important in this cohort. So things like stigma could affect also just student engagement. So students could just not be taking the test seriously. They could be disengaging, which is something that we know is the case with COVID. And that's why, for example, colleges decide not to use scores and look at essays and so on. So what are your thoughts on that, on the fact that perhaps educational outcomes are not the thing that we should be looking at when we think that the mechanisms are social and had to do with stigma or what sociologists used to call anomie?
Yeah, those are good questions. So for the first one about Flint, I mean, so I think when I went there, and actually I might be going back relatively soon, but I think there's three things that are like noteworthy at least. Like the first one was that definitely people in Flint are like quite wary of like the extra attention that like other people outside of Flint have gotten, sort of like basically people coming in to study Flint, the idea that like sort of Flint represents something to the like larger country. I think there's a way in which like the community has really sort of tightened and feels people are very determined to stay in Flint. And I think people are a little bit skeptical of sort of outsiders who are interested in Flint now after the crisis. So that's true. I was surprised at, in some ways, the community, the members that I talked to, which were mostly at the School of Public Health, feeling sort of reassured by the results. Like in one sense, there was something like what we experienced is real. Like there wasn't like we were actually affected. And then on the other hand, I think the fact that like it's not so clear how you remediate like sort of lead exposure, can you sort of undo the negative developmental effects of lead? I think it's more of a question mark. That doesn't mean that we couldn't invest extra money into kids, but I think the fact that like what actually kind of mattered or might have mattered to some extent for many of the kids was the crisis was reassuring in the sense that it's like, oh, okay, look, we actually have a toolkit for like in the world of dealing with like children who are disengaged or children who feel marginalized. So it was a really good experience. Can you remind me of the second question?
Yeah, so if it's stigma or it's social disaffection, right, that is the mechanism, it might be that the tests are no longer sort of
Right.
capturing like something about learning or skill, or they're just capturing a
Totally,
relationship
yeah.
to schools.
And I saw an interesting paper recently showing that certain maybe national test score gaps could be explained if you put stakes onto the test. And so if in some sense maybe different countries were different in their investment in performing well on tests, and that explains some of the NAEP differences. I didn't read into that, but yeah, I think that's an interesting idea. So what if there actually wasn't true, there's not some psychological construct that involves math performance that declined in Flint before and after? What if the students were just less motivated to kind of even fill in the bubbles on the test? I think that's an option. I don't think there's a way that we can distinguish that. Yeah.
But I think the timing, the big declines happened before anybody knew, right? So it wasn't public knowledge.
Yeah, I mean, I guess the question to some extent is how much
Unless
were
the
people,
brown water was so
That's
discouraged.
right. Yeah, how were people feeling sort of in that first kind of year and a half period versus in the national crisis period?
So they had nasty water in the first year and a half.
Mhm.
So they had a Flint crisis. Before the national crisis, they were probably very aware that something was not happening.
That's right.
So
Maybe it was the dirty water.
But I guess maybe to Tom's point, there could be something different about there's a start of one kind of crisis in mid 2014, and then there's a start of kind of a bigger, different kind of crisis in 2016, and it's not totally clear how each mattered and to what extent. Yeah, Andrew.
But then, I'm trying to resolve Tom's comment, right? Because the decline in math achievement was right at the beginning, and then it sort of stayed stable and maybe just got a little bit more precise. So if that's the case, I really like your cross diagram. But if that's the case, then it suggests that it's psychosocial due to the dirty water, not psychosocial due to the crisis. Is that right?
Yeah, that's right. I think the individual years are less precise. We only have 4 years of data post-treatment. I think, or maybe it's 5. I would need to check. But you can see from the confidence intervals on the figure that the individual years are much less precise than in the paper we present the average treatment effect. And so I do agree that if I look at those figures, the drop happened immediately.
Right.
And again, there was a little bit extra time in between those two tests because, while one was in, 2014, one was in 2015, there was actually a year and a half between those two tests because of the change in test schedule. But yeah, so I don't know. Maybe there's a statistical test to see if what we can kind of know quantitatively. But yeah, it's a good point.
My understanding is that the effects of lead operate largely through behavior. I could be wrong. And my sense is if you have someone misbehaving in the classroom, then there's going to be externalities to that other people might not be able to concentrate. In a sense, this is psychosocial.
That's right.
So
Yeah.
That's very different from stigma.
I think lead both sort of affects sort of cognitive abilities and executive functioning, self-regulation, and so this is also why there's been sort of research linking lead to crime later in life, and it's not just crime in general. It's violent crime typically, and I think it's there's this idea that lead sort of lessens our ability to control our emotions in a way. So I think
your comfort. That would explain why you would have no difference between comfort.
right. So it is if there was if something about the within Flint experiment is effectively if SUTVA is violated, if there's spillovers in a meaningful way, then that could be a way that sort of lead actually mattered, but it mattered sort of for the whole town, and we just can't see that. That's a good point.
So I just wanted to thank Sam for the talk. Actually, it was a great combination of technical talk, but also of a substantively important and engaging questions.
Yeah. Well, thank you so much for having me.
And our next talk in the peer seminar series is November 8th with Christina Brown. She'll be giving a talk entitled Cognitive Endurance as you have. So thanks everybody, and see you November 8th. See you all.